This video has been created in order to enable online first semester physics courses that include at-home labs. Such courses may include lab kits provided by commercial vendors who assemble the kits, provide procedures, and most importantly, deliver the kits all over the world. Universities and colleges that offer these courses are really dependent on this distribution capability. They really can't do it themselves. Because there's a lot of pressure to provide affordable courses to students, the quality of the materials in the lab kits is generally low. Nonetheless, good experimental results can usually be achieved if the students exercise some care in the experiment setup and the data collection. Unfortunately, the procedures provided by the lab kit suppliers frequently are poor. Sometimes they direct the students to poor practices so that results turn out to be unnecessarily poor. Sometimes they have wrong physics, formulas, and derivations. This is particularly egregious because they teach the students incorrect physics. Occasionally, the procedures don't even work. This video is a consequence of a vendor procedure that does not work. Let's begin by looking at the simple Atwood machine. The simple Atwood machine consists of two masses connected by a string and hanging over a pulley. If mass M2 in this picture is bigger than mass M1, then mass M1 will accelerate upward and mass M2 will accelerate downward. It seems like common sense. We can just simply write down all of the arrows that indicate the forces on the blocks. If we look at mass M2, the acceleration of gravity is pulling downward and the tension of the string is pulling upward. And so the equation of motion, Newton's second law, is simply that the tension pulling upward is positive. We will take positive to be upward in this diagram. And mg pulling downward is negative. The acceleration is downward, so we give it a negative number as well. And so we have the equation T minus m2g equals minus m2a. Now mass m1 is going upward. The tension is still pulling upward. m1g is pulling downward. The acceleration is upward. So we have T, the upward force, minus m1g is equal to m1a. Now if you simply subtract equation 2 from equation 1, you get the relationship that the acceleration is m2 minus m1 over m2 plus m1 times g. And this is what you expect. If these two are equal, then it's 0. Well, that's normal, right? Now let's modify this simple Atwood machine. We still have M2 pulling downward, but M1, instead of just moving vertically, is sliding on a ramp. Well, then the tension is still pulling up on M2, and M2g is still pulling downward, and the acceleration of M2 is still downward. The block that's sliding on the ramp, its acceleration is along a line that's parallel to the ramp surface. M1g is the gravitational force pulling downward. It has a component, m1g sine theta, that is pulling parallel to the ramp but backwards. And it has another component that is perpendicular to the ramp, m1g cosine theta. And the tension is pulling upward. There's also some friction, and the friction is pushing backwards, and we'll come to that in a bit. So in this case, m1 times the acceleration upward is equal to the tension that's pulling along the ramp minus the friction that's pushing back and minus this m1g sine theta, which is this component of gravity that's also pushing back. If we assume that the friction is 0, then Newton's second law applied to the sliding mass is that m1a is equal to the tension pulling along the ramp minus m1g sine theta. And Newton's second law for the mass that's falling is that minus m2a is equal to the tension minus m2g, just like it was in the simple Atwood machine. Now, if we subtract the bottom equation from the top equation, we get that m1 plus m2a is equal to g times m2 minus m1 sine theta, and we get this expression for the acceleration of the sliding mass. The assumption that the friction can be neglected is generally not a good assumption. In fact, what prompted the production of this video was that a lab vendor provided a foam board to be used for the ramp. And certainly a foam board is not a hard, smooth surface where the friction would be low. So in the event that we have friction that is not negligible, then we will have that m1a is equal to the tension minus m1g sine theta minus the friction that's pushing back. And of course the falling mass is still the same equation as we had before. Now the friction is given by the coefficient of kinetic friction, mu k, times the normal force. And if you look at the diagram, the normal force is m1g cosine theta. So if we put that together, we get the equation that m1 plus m2 times the acceleration is equal to the acceleration of gravity times m2 minus m1 times the sine of theta plus the kinetic friction coefficient times the cosine of theta. What we want to do is set up an experiment where we can measure the acceleration of the sliding mass and then verify this equation that relates that acceleration to the acceleration of gravity. Unfortunately, we can't do that because we don't know a value for the kinetic friction coefficient. So then the question becomes, how can we figure that out? The way to do that is to run two cases where the sets of masses are different. Let's call them case alpha and case beta. In case alpha, we will have mass m1 alpha and m2 alpha. And in case beta, we'll have mass m1 beta and m2 beta. So we can write the equation down for both cases. And then if we divide, the g's will go away and an equation will remain that only has one unknown, which is the kinetic friction coefficient. And we can solve that and get a value. Let's call the expression on the left-hand side R. It's the ratio of the sum of the masses from case alpha times the acceleration that we measured for case alpha divided by the sum of the masses for case beta divided by the acceleration that we measured for case beta. So we know all those numbers and we can calculate it and get a number for R. And if we do this, then writing the rest of the algebra is just a lot easier. So once we do that, and we put R in here, then it follows that the expression for mu k is given below, and the expression for gravity is given below. And then we can basically do the process of measuring distance versus time for case alpha, measuring distance versus time for case beta, and then fitting these data sets with a parabola, which determines, according to the coefficient of the quadratic term, the accelerations A alpha and A beta. Then we can calculate R, and then we can calculate mu k, And finally, we can calculate G. So now that we have the theory, let's set this thing up and see how it works. Here you see a picture of the basic setup. It is a smooth board that rests on a prop so that it's tilted. It has a pulley attached at the top, a beaker that slides on the board, a string that goes from the beaker over the pulley. You'll also see that I've hung a string straight down. That allows us to measure a height and a distance that make up a right triangle so that we can calculate the angle of the board. You may not have a board like this around. The important thing is that the surface has to be stiff so that it doesn't flex, so that it's flat, and smooth so that the beaker will slide on it nicely. The foam board that was provided by the vendor flexes and also has a rough surface. So it's not a good idea. But you might lay a piece of cardboard, for example, if you could find a nice smooth one, over the top of it, and that might work just fine. The point is, you have to find something smooth and stiff. A little care is needed when attaching the string to the beaker. Simply tie a loop around the beaker. But if the string is too high on the beaker will want to tip forward toward the pull of the string. So you need to attach at approximately the elevation that the string is as it goes over the top of the pulley. And you can see that I've put some tape on here to keep the string at the right elevation. That way, when it pulls, there will not be a tendency to tip the beaker over. The lab kit comes with some washers that will be used as the weights. We will place washers inside the beaker and we'll tie washers at the vertical end of the string. We need to know the weight of these washers. The lab kit also comes with an electronic scale. I don't have it, but I do have a kitchen electronic scale, and it doesn't measure to a milligram, but if I take 15 of these weights and stack them up on the scale, you can see that it comes out to 408 grams, and all I have to do is divide by 15, and I'll have a good average weight for each of these. And I can use that when I decide what the weights are in the sled and also what the weights are that are hanging. Now we're going to want to measure the position of the beaker as it moves. In other words, we want to collect data, which is the distance moved versus the time. To do that, we need to put a tape measure on the slide board. And so here you see the tape measure has been pulled out, and I used some of this blue tape at the two ends of the tape measure so that it won't move. But we're going to need some kind of a pointer as well so that we know where the beaker is, because it's going to be a few inches away from the tape measure. And so here you can see I've just taped a pencil to be a pointer on the back side of the beaker. And so you can imagine that, as we'll see in a bit, as this thing slides along, we'll see the pointer move along the tape measure, and we'll be able to observe the distance traveled. We'll do this by using a cell phone to take a video, and then we'll play that video back one frame at a time so that we see still pictures of the pointer over top of the tape measure, and we can write down the position. The sliding mass will be the beaker with some washers inside of it. Now we've already figured out how to get the weight of the washers, but we must also know the mass of the beaker with the attached pencil, and then we'll have to add them together to get the total mass of the sliding piece, or in other words, the total of M1. And here you can see that the beaker with the pencil attached to it has a mass of 29 grams. For case alpha, 3 washers were placed in the bottom of the beaker, and 3 washers were tied at the hanging end of the string on the other side of the pulley. As you can see from this frame from the video, the beaker remained at rest. The pull was not sufficient to overcome the static friction. A very slight push was given to the beaker as shown in the frame on the left in order to break the static friction. Once that was done, the beaker began sliding nicely. The picture on the right shows one of the frames from the middle of the video, and you can see that it is slightly blurred. And however, it's clear that the pointer is slightly more than 23 inches, perhaps 23 1/8 or 23 1/4 inches. In order to take one of these videos, you have to hold the cell phone video in one hand while you nudge the thing with the other, and you have to move the cell phone along with the beaker in order to keep the blurring down so that you can actually read the tape measure. It may take you 2 or 3 or 4 tries before you get a satisfactory video. A normal cell phone video has 30 frames per second, so the time increment between frames is 0.033 seconds. If you run in slow motion mode, that will be 300 frames per second. But then the number of frames you'll need to count becomes very big and very time consuming, and it's really not necessary to have such good time resolution here. So these videos were normal videos with 30 frames per second. They can be played back 1 frame at a time. To do that, I used free video to JPEG converter, which is freeware that can be downloaded, and it produced a folder containing a couple hundred pictures from each video. Starting a couple of frames after the one on the left, each frame was inspected and the position of the pointer was written down until the beaker collided with the pulley. There were a total of about 60 frames, so this total motion took somewhat slightly less than 2 seconds. For case beta, 3 washers were placed in the beaker, but 4 washers were tied to the end of the string. In that case, the beaker would not stand still at the start. I had to hold it. And then when I released it, it slid quite quickly to the end of the board. It took about 4 tries before I was able to move the cell phone fast enough to get a reasonable video, but I did get one. I also ran one more case, which had 4 washers in the beaker and 4 washers hanging, for a total of 3 cases. In each case, the videos were played back a frame at a time, and the positions were listed. In the case of the very fast motion, it was not possible to determine positions in the latter part of the motion. The thing was just moving too fast, and the picture blurring was just too much. This is a screenshot of the Excel spreadsheet. In the upper left corner, you see the length, 22.56, of the base of the triangle, and then the height that was measured, which means that the angle in radians was 0.37 radians, or 21.2 degrees. Then over here, and where it says case 1 inches, case 2 inches, case 3 inches, those columns have the readings of where the pointer was on the tape measure. And then those are converted into meters over here on case 1 meters, case 2 meters, case 3 meters. And then this is the time in this column, which is 33 hundredths of a second for each frame. The time column and the 3 columns that are the distances in meters were selected, and then a scatter chart was made, and this is the result. And you can see the blue is the case where we had 3 washers in the beaker and 3 washers hanging out. And the motion was pretty slow. 1/2 of the acceleration would be 0.1066. The 4 washers hanging and the 3 inside the beaker is the orange curve, and that fits really quite good. And 1/2 the acceleration is 0.5455. In the case where there were 4 washers in the beaker and 4 washers hanging is the gray here, and the acceleration will be twice 2.31. So the curves fit quite nicely, and we have very good values for accelerations. So we should be able to use those now to go back to the spreadsheet and program the formulas to calculate the coefficient of friction and also calculate experimental values for the acceleration of gravity. So now returning to the screenshot of that portion of the spreadsheet, you'll see this area over to the left here that says case 1, and I've recorded the mass that was sliding, the mass that was hanging, and the acceleration, which is 2 times the slope 2 times the value on the graph, and that's 0.213. And then you'll see case 2, where we had the 4 washers hanging and the 3 washers in the beaker, and you see that we have recorded their masses and the acceleration. Then the formula for that ratio that was way back in the theory is in this cell. The numerator for the expression in the coefficient of friction is in this cell, and the denominator is in this cell. And on the screenshot, I can't show you how those formulas are built in very well. Then when we take the ratio of 1 to 2, we get the coefficient of friction is 0.35. And that's right in the range that we kind of expect. That's pretty typical of friction values. And we get a value for G of 7.29 meters per second squared. If we compare case number 3, which was the 4 washers in the beaker and the 4 washers that are hanging, to case number 1, then we do the same thing. We have the masses recorded, we have the acceleration, we calculate R and the numerator and the denominator, and we get the coefficient of friction is 0.36, which is really quite close to the 0.35 that we had up here, certainly within the experimental error. And what you can't see because it's cut off is that the value of G turns out to be 8.82. So this one comes a little closer to the expected value of 9.8. But the point is that we got very consistent values for the coefficient of friction, and we got reasonable values for the value of G. And so that pretty much concludes how you do this thing. When you do it in class, I will provide this spreadsheet, and you can simply replace my data with your data, and the calculations should automatically take care of themselves.